Hi everyone, my name is Casey Morrison and I'm a systems engineer at Astera Labs. My colleague Pulkit Khandawal and I put together this presentation for this session of OCP, which is entitled Signal Integrity Challenges for PCI Express Gen 5 OCP Topologies. The problem statement that we're addressing in this presentation is one of signal integrity. Going from PCI Express Gen 4 at 16 gigatransfers per second to Gen 5 at 32 gigatransfers per second, the PCI Express standards body has increased the channel loss budget from 28 dB, as shown in the table on the left, to 36 dB. However, the physical size of servers hasn't really changed that much. And as we'll see in future slides, the physical distance that the signal can travel from, say, the CPU to an add-in card or a riser card is greatly limited at the higher 32 gigatransfers per second speed. As I mentioned, the total budget for Gen 5 is 36 dB. Interestingly, a full 9 dB of this budget is consumed just by the CPU root package. The endpoint package is allocated 4 dB. Connectors are generally allocated 1.5 dB. And add-in cards are allocated 9.5 dB. This leaves just 16 dB for the system board, including any custom riser cards that a system board implements. And as we'll see in later slides, achieving a system board channel with just 16 dB is particularly challenging, given the topologies that exist, the layer transitions that are necessary, the vias involved with that, the AC coupling capacitor pads, etc. And on the right, what I'm showing is an example from OCP. This is the Olympus project, just highlighting some of the typical distances between processors and the various add-in card slots, ranging from about 6 inches to up to 10 inches. So what are the ways to solve these signal integrity challenges which will exist for PCI Express Gen 5? What this is trying to show here is the various components of your end-to-end channel adding up as the blocks stack on top of each other. And this is showing an example case where the aggregate loss of all of the different components exceeds the 36 dB budget. You have the root package at 9 dB, the system board at dozen or so dB, connectors, add-in card, etc. And in this particular hypothetical case, the aggregate loss is over the spec limit. Now, what can you do to solve this? Well, one way is to upgrade the baseboard PCB material from a standard enhanced FR4, for example, to something lower loss like a Megtron 4 or Megtron 6. Many discussions in PCI-SIG and other forums talk about materials called low loss and ultra low loss materials. These aren't very well defined, but in general, you can see about a 20 to 30% improvement in loss on the system board itself for low loss material, and maybe an additional 30 to 40% improvement for ultra low loss material. And going to those lengths may improve your scenario and give you some margin below that 36 dB. However, there's going to be a cost involved with upgrading your large baseboard PCB to an expensive material. And in some cases, that may not be enough to solve the problem. Another possible option is to segment your channel, specifically the ones which are over the budget, into two portions by using a protocol-aware retimer. The retimer basically cuts the channel in half so that you have two link segments, each of which would now generally be well within the 36 dB total end-to-end loss budget. So going in more detail about the PCB material trade-offs, as I mentioned, there's no industry standard definition for what is mid-loss, what is low loss, and ultra low loss. And the specific insertion loss and other properties of these materials will vary depending on manufacturer. So system designers really ought to determine loss numbers for their system based on what is representative of the specific materials that you plan to source. The table below shows an example of representative materials in systems like servers, and I've categorized it as mid-loss, low loss, and ultra-low loss. And it's roughly similar to Megtron 6 type material for the ultra-low loss case. One important thing to consider in the material selection is the degradation in characteristics, specifically insertion loss, from nominal to worst case conditions, worst case being high temperature and high humidity, for example. And these percent degradations here are based on a 16 gigahertz Nyquist frequency. So for a mid-loss material, enhanced FR4, for example, you can expect around a 16% degradation in insertion loss at Nyquist, going from room temperature conditions to high temperature, high humidity conditions. What this boils down to is, if you look at the right half of this table, these are the loss per unit length for the different materials under worst case conditions. And the far right column, 16 gigahertz, is for 32 gigatransfers per second. And as you can see, even the ultra low loss materials are in the 1+ dB range per inch. So what are the reach implications for PCI Express Gen 5? Well, we just saw what the loss figures are for typical materials. Another point that I wanted to make is, if you design a system to operate at the specification required bit error rate of 10 to the minus 12, then just based purely on the numbers, based purely on the math, the link will enter into recovery at a rate of about once every 10 seconds. And you will have a TLP replay at a rate of about once every second. Now this is for a by 16 link running at 32 gigatransfers per second. That's just the fundamental reality we're dealing with for a 10 to the minus 12 bit error rate. Now, this same analysis, which by the way is from my colleague Pulkit Khandawal from a PCI SIG DevCon presentation in 2019, showed that if you can reduce the channel loss just by a few dB, the bit error rate can improve significantly. And this reduction in channel loss below the maximum allowed 36 dB is what we like to refer to as safety margin. It's basically a self-imposed reduction in the loss limit that you target for your system design to effectively give you peace of mind. So if you factor in a safety margin of about 15%, then at 32 gigatransfers per second, you're roughly dealing with the lengths shown in this table below. Meaning you can go from the CPU to the slot and still have margin for the adding card at about 3 inches for mid-loss material, 5 inches for low-loss material, and about 8 inches for ultra-low-loss material. And as you saw in the previous slide, 8 inches may not be enough for many server baseboard designs. So I wanted to show some OCP topologies and how these realities may impact those topologies at Gen 5 speed. For Gen 5, because of the fact that we saw that even with ultra low loss Megtron 6 material, you cannot meet your budget across worst case conditions with safety margin beyond 8 inches, we expect, and we've seen many cases where retimers will be used on the baseboard itself. And in this example, I've superimposed a picture, a block of a retimer being used on this Olympus 2-socket server for specifically the 10-inch case. But arguably, all of the cases 8 inches and above may require a retimer to segment that link into two. This is another type of system where retimers would be used even for Gen 4 speeds. This would be just a bunch of drives or just a bunch of flash JBOD, JBOF type system. Here the block diagrams are from the Facebook Lightning project. And here what the retimer is basically doing is helping to span the distance from box to box, from the hosts on the left through some type of cable, mini SAS HD in this particular example, to another system which has a PCI Express switch connecting to many different SSD drives. And in this case, one feature of a retimer which would be required is to support bifurcation, to support multiple by 4 links within a single device, because SSDs are typically in the by 4 or by 2 width. The last example we have here is for an Accelerator baseboard. This is an emerging application, emerging form factor, and the diagram shown here is showing how retimers can be used both between the Open Accelerator modules and the host interface, so effectively helping to span the distance between the host through some type of cabling or backplane to the Open Accelerator modules, as well on the bottom side between the Open Accelerator modules and some type of an expansion port like a QSFP DD form factor. And what's critical for this application and other applications in the previous slides is low latency. The bandwidth is obviously important between the OEMs and the hosts or other systems, but just as important as bandwidth is latency, especially when these applications require new types of functionality such as cache coherency, memory sharing, resource sharing, and things like that. Latency through the retimer device is very critical. So how do you determine if a retimer is required? There's generally 2 ways to do this. One is a simple channel loss budget analysis. That's what's shown on the left. And this is a very straightforward process where you say, okay, my total loss budget is 36 dB. You might want to back off from that by 15% for safety margin. But then you say, okay, my total budget is this. I have an allocation for the root port package of 9 dB, the non-root package of 4 dB, connectors, etc. And then you see what's left over for your system board. And that plus the loss per inch of your system board material can roughly tell you how many inches you can go on your baseboard. The other approach is to do a CSIM analysis. CSIM is a statistical eye analysis simulator. It's not a bit-by-bit simulator. It's a statistical simulator, but it's more thorough than just simply adding up dB loss at Nyquist figures. And that would be recommended, especially if you have S parameters for your particular topology. This slide here is showing an example of how this simple channel loss budget versus CSIM analysis can compare with each other. So on the far left case, we have a very smooth loss channel, 36 dB right on the dot at 16 gigahertz. And you look at the loss at Nyquist and you say, yep, this is 36 dB, it should be fine. And if you simulate that same channel in CSIM, lo and behold, it tells you that it is basically fine. It has marginally failing eye height and passing eye width. However, if you look at another case in the middle where the loss at Nyquist is only 33 dB, you might falsely assume that this is going to be okay. But if you run that through CSIM, you'll find that because of the reflections, the high return loss of this particular channel, you're actually failing on the eye height and eye width requirements that PCI Express sets forth. And just to complete that comparison, if you take a smooth loss 33 dB at Nyquist channel and run that through CSIM, you'll see that you have lots of margin. So not all channels are created the same. Not every 33 dB channel is the same. CSIM helps to understand the impact of things like crosstalk and reflections. So what we would like to call for in terms of action is, of course, we want to encourage participation in the OAI, PCIe card, and server communities. We also want to gauge interest for a possible new subgroup, a connectivity subgroup, basically focusing on specifying high bandwidth, low latency interconnect solutions between OCP systems, like the Open Accelerator baseboard, other kinds of systems, JBoss, JBOG, etc. This could involve or include specialized extension cards that have different form factors, like SlimSAS, Oculink, or maybe even an OCP NIC form factor. If you do have interest in such a thing, please contact me, casey.morrison@asteralabs.com. Otherwise, there's some links to other helpful information, and I really appreciate you joining this session. Thank you. Hi, everyone. This is Casey Morrison here. Just wanted to see if there's any questions on the line that Pulkit or I could answer for you. Okay, there was a couple on the posts that I guess we could read and address live. So the most recent one was about PCIe retimers on the Open Accelerator baseboards in the block diagram being connected to QSFP DD connectors. I realize that in that particular block diagram, that specific interface is actually used for other protocols. So it may not be a PCIe retimer that's used on that particular interface. But I will say that in the various systems that I've come across, working with the Astera Labs retimers and a number of different systems, I have seen customers use QSFP DD as a mechanism for carrying PCI Express Gen 4, for example. So as a connector and a cable technology, I think it's sufficient to support that, but it's probably not the most common interface used for external cabling. Another question just came in. What about equalization? Could that be used to and optimized to mitigate the high loss of the channel instead of using retimers? So very good question. At Gen 4 and Gen 5 speeds and even Gen 3 and below, there is a heavy amount of equalization being performed by the transmitting device on the CPU, for example, and the receiving device, the receiving SerDes on the endpoint, and vice versa. There's a 3-tap FIR in the transmitters being fine-tuned by the receiver during the equalization process, and each receiver typically has a CTLE to perform some equalization, multiple taps of DFE, etc. So that is being employed, and even despite that, the physical channels are exceeding, in many cases, the 28 dB budget of Gen 4 and 36 dB budget of Gen 5. So in those cases, of which there are many for different topologies, people are having to consider new PCB materials, connectors, and or retimers. Okay, well, we'll try and address the remaining questions on the chat window. And again, just want to thank everyone for joining and participating.